To start, I'll take do an example from the 6-2 homework. If anybody has a 6-2 problem that you're interested in seeing, be happy to do, just say one of those, and then we're on to another way of calculating volume, or another situation that we would have to calculate volume in. It's not the same way, but it's, like a little different, in that there's no rotation happening. So if anybody has something from 6-2 that they're like, ooh, yes, I was working on that assignment and I got to number blah, and I was like, I don't know what to do with this. Or I thought I did it and I didn't get it. If not, I'll just pick one. That's fine. See some people eagerly digging through their notebooks. I'm going to pause here for a minute, see if there's a specific one, so it's a little more meaningful. But if we don't find one, that's okay. I can just pick two. It's not a big deal. Anybody got one? Okay, I'm picking. So no problem. Okay, that'll do. Grab one of these. I'm going to pick 15, I think. Sounds like a good one. So this is 15 from 6.2. So we're looking at the region formed by the curves y equals x cubed, y equals 0, x equals 1, and we're rotating about the line x equals 2. Pretty good with the initial description of what we're doing. So I'm going to start by sketching myself a picture of kind of what's going on here. So I'm going to start by just graphing y equals x cubed. Now I could do this on my calculator, but this is an easy enough function that I know what it's going to look like without it, right? So if I plot some points, I got 0, 0, 1, 1, and then 2, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's deep enough. Everybody's okay with that part. And then I have the line y equals 0. And then x equals 1. So the region that we're interested in is this little guy right here. That's bounded by x equals 1, y equals 0, and y equals x cubed. Everybody feel okay there? And then we're going to rotate this about the line x equals 2. So I'm going to think about this like sweeping in a circle, and I'm going to look at the solid that's made. I'm going to imagine this in my mind's eye. When I do that, what is this thing going to look like? Got a hole through the middle, and it kind of flares out at the end, right? You can kind of see that as you spin it around through your mind's eye and think about like the solid formed by that two-dimensional shape, like spinning in a circle. Really helpful if you're able to visualize that. Okay, so now that we've established what the solid looks like, what type of cross-sectional area am I going to have for this? So if I start slicing this to compute a volume, let me ask a different question then, since nobody wanted to answer that one. When I'm slicing, should I be slicing horizontally or vertically? Horizontally should be the answer. Very good. You always want to slice perpendicular to your axis of rotation. Okay, if we do that, what are the slices going to look like? Are they going to be, they're going to be a washer shape. Very good. So I want to make we're going to do this using washers. Since I'm slicing horizontally, I'm going to be integrating with respect to the y variable, because when I make my horizontal slices, I'm moving up and down. Is everybody okay with that? So really important at the start that we're able to visualize what does this situation look like? What is the shape of the solid? Should I be using washers or discs, or in the coming lessons, a third choice? And then should I be integrating with respect to x or y? Okay? So what I'm going to do now is I'm going to draw in, well, maybe before I do that, let's do this first. So since we're doing washers, I know that my area is pi r squared for the outer radius minus pi r squared for the inner radius, right? So what I'm going to do now is draw in a arbitrary, typical, let's do the outer radius first, I guess. Everybody's okay with that? So the radius is always going to start at our axis of rotation. So in this case, that would be the line x equals 2. So this would be like an R outer. Is everybody okay with that? If I look at that line, it's a horizontal line. So the y coordinates are the same. The x coordinates are different, right? So the length of that R outer is just going to be the difference in the x coordinates. Everybody agree with that? So that's really easy for the first one because it's on the line x equals 2. The x coordinate there has to be 2, right? For this line, though, or for this curve, the x coordinate is changing depending on where we're drawing that radius at. So remember that because it's on the curve y equals x cubed, this guy is written as like x comma x cubed. It's okay here. But I need to have this with respect to y. So I put the y there. So I need to take y equals x cubed and rewrite this as x equals the cube root of y. So we're just changing and treating the y as the independent variable, and the x is the defect. So my outer radius is going to be the radius on the right, or the point on the right, minus the point on the left. Pretty good. So it would be 2 minus cube root y. Do you feel okay? Am I going slow enough in explaining? I'm trying to be really thorough and talking about how I know things, right? Is it doing okay? Stop me if I go too fast or I need to re-explain something, Sam.
Where does the
2 minus cube root y?
Yeah.
So this RO is going to be like x2 minus x1, right? Because you're looking for the length of that segment. Since it's a horizontal line, I just need to subtract the x coordinates. Does that?
Yeah, I thought it was at 1.
Okay. Now it's time to draw in our inner. So I think I have enough room that I can just kind of slide that in underneath it. Oops. So again, I'm going to draw just like an arbitrary inner radius. Now this is even easier, right? Again, we have some point 2 comma whatever, and this point over here is just like 1 comma whatever. How long is that radius? 1. It's the same length no matter what slice we're taking, because those 2 lines are just vertical lines. Does that feel okay to everybody? Okay. Right, so our volume formula in general is the integral of the cross-sectional area, right? Since we did washers, our cross-sectional area is pi r outer squared minus pi r inner squared. And then, since we're integrating with respect to y, it's going to be a dy. The last thing I need are the bounds for my integral. Since we're integrating with respect to y, we start slicing at y equals 0, and we continue slicing all the way till we get to y equals 1. So that's my setup. If this is on the AP exam, and you're in a calculator loud section, what time is it now? It's calculator time. I'm just typing this integral into my calculator and pressing enter. I have no interest in doing this by hand unless I must, right? Now, a question at this level, this is an easy enough question that we can do by hand. I'm going to go ahead and do it by hand also, just to help refresh our memories about how this integration process by hand works. When I give you your exam for this class, these volume questions are going to be done with the calculator. So you're going to have points for identifying the type of cross-section to use, what variable you're integrating with respect to, the expression for the radius, like the bounds of integration, like the actual full setup of the integral you're typing into your calculator, and then your final answer. So you're just going to have like setup points because the calculator is going to do all the integration for us on this. That allows us to do more questions in a time setting. Is everybody okay with that? Okay. And also include things that like maybe the integration is just not feasible for us to do, period, right? Okay, so let's start our integration of this. Again, we're going to do this by hand. The first thing we want to do is pull the pi out, and you said make it 2 separate integrals. We can do both at the same time. That's fine. I would not separate it yet, though. It's okay to do it. I'm not going to, because what I would do before I try to separate it is I want to FOIL this stuff out and see if there's like terms to combine, because I might be able to do this with just one less integral or something, or a bunch of stuff might cancel out and good stuff might happen. I don't know. I mean, I know, but I don't know just from looking at it if if it's going to be really advantageous to leave it all together and combine like terms before I separate. So I would simplify inside the integration before I separate into different integrals. Okay? But not wrong to do that, right? So let's FOIL this out. And I'm going to rewrite these cubed roots as fractional exponents. Now I did that quickly in my head. Does anybody need me to grind out the FOIL by hand? You guys can see it. If you change your mind, I'm happy to do that, but again, I don't want to like get overwhelmed in detail here. If it's something that's like, yeah, that's trivial, you can handle that. If you look inside, is there any other simplification that can happen? I see a 4 and a -1. Let's combine those together, right? That's going to eliminate a need for us when we distribute our integral symbol through. That cuts out another integral that we'll need to deal with, right? So that's nice. Let's do that. That saves us a little bit of time. You see what I'm saying by waiting to separate? Because if you don't do that, then it's not obvious to reconnect them together to combine those. Everybody's good? Okay. So let's go ahead and distribute that integral symbol through, and we're going to pull out some constants in a couple of places. And I got to be real careful here that pi comes with me when I distribute the integral through. It's an easy mistake to make, is not bring the pi with me. Everybody feel okay with what I did there? Why didn't I bother to pull the 3 out front of the first integral there? Is it wrong to do it? Definitely not wrong to pull the 3 to the front. The reason I don't is because you'll just have the integral of dy. What's the antiderivative of dy? The dy. Now that's not super obvious because it's 1 times dy. That's why I left the 3 in there, because it's the antiderivative of 3, you would say 3y automatically. That's why I'm leaving it. If I pull the 3 out, then it becomes like, if you think about it for a minute, like, okay, that's obvious why it has to be y, but at first glance, you see that and you're like, I don't know what to do with that, right? All right, antiderivative time. So we have 3 pi from 0 to 1 minus 4 pi times the antiderivative of pi to the 1/3 is? Yeah, 3/4 y to the 4/3. And then the antiderivative of y to the 2/3 is? Does that look all good? Yeah.
Oh,
Hey,
can you just show how you got 3 pi again from the pi?
Oh, sorry. 3 pi 1. Sorry. Should be a 1 there. Thank you.
Yeah.
That's what you're asking about, right?
Yeah.
Yeah. What happened to the y? Good question. It's supposed to be there. All right. Now we just plug in our zeros and ones. And I'm going to do, I'm going to do that just to make my life easier. Pretty good. 1 to any power is to the 4/3 or 1 to the 5/3 is 1. 0 to the 4/3 or 0 to the 5/3 is 0. So I have 3 pi minus 3 pi plus 3/5 pi. Right. 3 pi minus 0, and minus 3 pi minus 0 plus 3/5 pi minus 0. So just 3 pi minus 3 pi plus 3/5 pi. So 3 pi, or 3/5 pi. Does that feel okay? Again, notice the amount of time. Where do we spend the most time, really? And the setup, right? Because ideally, the integral, I would have done this in the calculator, if given my choice, right? We did it by hand because we can, and we've been talking about integrating by hand, and I want to do another example and just kind of show you what that looks like. But the setup, I spent a lot of time thinking about what does this thing look like, where the radius at, what integral or what variable am I integrating with respect to, what is the expression for the radius, what type of cross section am I going to have. I spent a lot of time thinking about all of that so I could package this together to set up, and then the integral goes pretty smoothly. If I screw up one of those earlier steps, I'm left with kind of a mess, and that's usually an indication that you've kind of goobered your setup. Does that feel okay? All right. Today, we're going to talk about another type of volume problem. This is kind of specific to the AP. These types of volume problems are not terribly difficult. They're a little hard to imagine.
That might be calculator. I'll do this one.
So again, this is not any more difficult than the type of setup we've done before, but it's different, and the wording is one where if you haven't done this and practiced this, it can be a little bit challenging. But if you're good at reading what they're giving you, the problem is going to tell you everything you need to set this up. Okay? So I have 4 examples here. We're just going to grind through these 4 examples, and I have a packet of AP practice problems for you guys to work on this exact topic, and that's going to be it. So this says, let R be the region, the first quadrant, bounded by the graphs of y equals x cubed and y equals 4x. As shown in the figure above, the region R is the base of a solid. For the solid, each cross section perpendicular to the y-axis is a square. What is the volume of the solid? So if we think about this, what's happening here, our cross sections are perpendicular to the y-axis. So that's like my cut that I'm making, right? That's going to be the side length of a square, and this square is like coming out of the paper at us. Come on now. Nobody wants these stupid arrows that we try to make. Right? So like if I had my cross sections down here, like it's kind of coming up out of the paper, like out of the board. Right? Can you see it? It has like a flat top to it. Anthony's shaking his head. He's the only one that can see it, apparently. But that's the idea. Here's the good news. Being able to visualize this, I don't need to set up this problem correctly. The words in the problem have told me everything that I need. Okay? So that's my cross section, perpendicular to y-axis. Because I'm perpendicular to the y-axis, what am I integrating with respect to? If I'm slicing this way, I'm integrating with respect to y, because I'm moving up and down with my slices. Does that feel okay? What is the cross-sectional shape? Tells me it's a square. It says the cross-sections are squares. That's my cross-sectional area. What's the area formula for a square? Side squared, right? You could say length times width, but they're the same in a square. So let's do that. So this measurement right here is my S.
That shape like the bottom of the.
That's the base of the solid. So it's like a flat bottom, and then there's like a square cross section is coming up. So if you cut it like this, and you look at the shape, it's a square. Does that feel okay?
Yeah.
So it's like coming up out of the screen at you. Is everybody okay? I'll show you guys a little video at the end to help visualize what's going on a little bit better, but it's not really that necessary to be able to do these efficiently. So don't get hung up on like what it really looks like. All right, so I need an expression for S in terms of Y, right? So this point is on, well, is it on y equals x cubed or y equals 4x? X cubed, how can I tell? It's the curved one, right? Okay, so this is like x comma x cubed, but we need to look at the change in x coordinates, so we need to rewrite this as a function of y, right? What will this be in terms of y's? Cube root y comma y. Everybody's okay? Let's do the same thing for this one over here. What will this be in terms of y? Oh my goodness, I'm doing the wrong problem. This isn't the one I wanted. Hold on one second, guys. I'm sorry. This is not. One second. Hold, please. Thought I had this all set. I didn't. So this is supposed to be this, and then this one would be that. Is everybody okay? Notice the problem changed here just slightly in that the functions are different. It's x squared and 2x instead of y cubed and 4y, but ostensibly everything else is the identical set. Sorry, I didn't have the right set of example problems. I picked 4 very carefully. Okay, so what is S going to equal? The right-hand function minus the left-hand function. Is everybody okay there? So my area then is going to be y to the 1/2 minus y over 2 squared. Okay there. So my volume is going to be the integral of y to the 1/2 minus y over 2 squared dy. And because we're integrating with respect to y, we start our slicing at y equals 0, and we end it at y equals 4. Everybody okay? That's our setup. Notice what's next to this problem on the screen? The little calculator icon. What's that telling me? Should be doing this with my calculator. Could I do this by hand? Yes, this is totally doable by hand. But let's not. So this was my setup. I think that's like 8/15 is what that works out to be. But that's my answer. Everybody okay? Notice how being able to see what the three-dimensional solid looked like was not terribly helpful to me, right? Like it didn't really affect much. The words basically gave me everything that I needed. Let's go to the next one. It says, let R be the region in the first quadrant bounded by the graph y equals 2 secant x, and the line x equals pi over 4, and the x and y axes. R is the base of a solid whose cross sections perpendicular to the x-axis are semicircles. What is the volume of the solid? So here they didn't give me a picture, so I need to kind of sketch one of my own. And they didn't give me access to the calculator for this, but that's okay. I can do this without a calculator. I would not ask you to do something this trig-y without your calculator. But we're going to do it without our calculator now. Who remembers what the graph of secant or cosecant looks like? They're like U's separated by asymptotes, right? A U that opens up and a U that opens down and then up and then down and up and down, right? So if I look at secant, secant is 1 over cosine. What's cosine of 0? 1. The reciprocal of 1 is 1, and then we're multiplying by 2. So like, there's the start, right? And then we're ending at the line pi over 4. What's cosine of pi over 4? Root 2 over 2. The reciprocal of root 2 over 2 is 2 over root 2, which simplifies down to just root 2. And then times 2. But 2 over root 2 is like root 2 times root 2, right? Is that okay? Or you can think about it as like 2 to the first over 2 to 1/2, and you subtract the exponents. Think about it that way if that's easier for you. Either way is fine. Does that look good? Okay. So this is my solid, right? The region bounded by those two lines in the x and y axes. And it says our cross sections are perpendicular to the x-axis. So we should be slicing vertically, right? So we're integrating with respect to x. Now it tells us that the cross-section shapes are semicircles. So what's the area there? for a semicircle. 1/2 pi r squared. What is this distance? The diameter, right? So if I slice the whole thing and I get a semicircle, you know, like the part coming out of the paper is like that, that distance is the diameter, right? Everybody okay there? Which I know is twice the radius, so the radius is going to be that distance divided by 2. Everybody good? This is a vertical distance, so we should be subtracting the y coordinates. This point down here is something comma 0. This point up here is on the curve. Y equals 2 secant x, so that's a point x comma 2 secant x. So what is my radius going to be? 2 secant x over 2. The diameter is 2 secant x. Does everybody feel good? So those guys can just kind of cancel out. So my volume then, I'm ready to go, is the integral of 1/2 pi secant x squared dx. And because I'm integrating with respect to y, I start my slice at 0 and end at pi over 4. What's the antiderivative of secant squared? Tangent oops, that's supposed to be pi over 4, right? Tangent of pi over 4 is 1, and tangent of 0 is? So my answer should be pi over 2. Everybody okay with what I did here? Am I going too fast? You tell me. I can pause, I can slow down, right? Or take more time inside of the problem. Keep going. Okay. 3 says, let R be the region in the first quadrant bounded by the graph of y equals square root x, the y-axis, and the line y equals 1. The region R is the base of the solid. For the solid, each cross-section perpendicular to the y-axis is an isosceles right triangle with the right angle on the y-axis and one leg in the xy plane. What is the volume of the solid? Start by drawing our picture. Square root of x, and then this is just 1. So there's 1, 1. So that's like our shaded region, right? Between the y-axis, the curve, and the line y equals 1. Do you feel good? So that's our base. It says we're slicing perpendicular to the y-axis. So we're going to be integrating with respect to y. Everybody's okay? And it says my cross sections are isosceles right triangles. What's the area formula for an isosceles right triangle? 1/2 base times height is for any right triangle. Since it's isosceles, it's really base and height are the same. So I'm just going to say like 1/2 L squared, where L is a length, right? How do I know that that's a leg length and not like the radius, or I'm sorry, the hypotenuse of the triangle? It says the right angle's on the y-axis and one leg is in the xy plane. So there's one of our legs, right, in the xy plane. Everybody okay with that? So it tells me that it's not the hypotenuse, which is great news for us because that would make this problem yuckier by a lot. Is everybody good? Okay, so I need to come up with an equation for L. So I need to look at the x coordinates that are changing. Well, it's nice, this x coordinate is 0. This x coordinate is, we need to rewrite in terms of y. We do have x square root x, but we want this as y squared comma y, right? So our leg length is going to be y squared minus 0. Is that okay? And I think we're ready to set up our integral. So the volume should be the integral of 1/2 y squared squared dy. And because we're integrating with respect to y, we start slicing at y equals 0 and end slicing at y equals 1, right? So slicing at y equals 0, stop slicing at y equals 1. And now that's going to leave us a pretty stinking easy integral. I guess we'll put it on out front. What's the antiderivative of y to the 4th? Y to the 5th over 5 from 0 to 1. So that's going to be 1 to the 5th over 10 minus 0 to the 5th over 10. So my answer is 1. So again, like there, how easy was that integral? Really easy, right? That was a really, really easy integral. The setup, much, much more difficult. On these non-calculator ones, that should be the typical feel, where the integral, when you get to it, it should be really easy. The number should be convenient on the AP exam. The antiderivative should be easy on the AP exam. Like the arithmetic afterwards should be nice. Now, if they give you the calculator symbol, do you want to do it by hand? No, because very likely the numbers are going to be nasty and the integration will be difficult, or maybe even impossible for what you're trained to do, as is the case in this problem. All right, last example here. It says the base of the solid is in the first quadrant bounded by the graph of y equals sine x and the x-axis from 0 to pi. So the graph of sine from 0 to pi looks like this. Everybody okay there? Again, that's, hopefully you remember from pre-calculus, and that's rather trivial. For the solid, each cross-section perpendicular to the x-axis, okay? So draw an arbitrary slice perpendicular to the x-axis, which tells me we're integrating with respect to x, is an equilateral triangle. What's the area for an equilateral triangle? What's my area formula I should use? Okay, so you could do 1/2 base times height, but what's the problem there? If it's an equilateral triangle, the height isn't one of the side lengths. Okay, what are our other area formulas for a triangle that we remember from pre-calculus or geometry? How about 1/2 AB sine angle C? Or Heron's formula, 1/2 S times S minus A times S minus B times S minus C square rooted, where S is the semi-perimeter. Now, which one of those two do you suppose I'm going to pick? Let me use this one. So A and B are side lengths of the right, or of the equilateral triangle, right? They're both the same. So if I call this L, what are the angle measures for an equilateral triangle? All 60 degrees. Oh, this is starting to look a lot nicer. What's up, Sam?
If A and B are equal, can you see the variable?
Yep, that's what I did.
Oh,
Right? Yes, correct. What's sine 60? Root 3 over 2. That's going to be the area formula that I'm going to use. Now, you can just remember the area from an equilateral triangle is root 3 over 4 sine squared, but that's where it's coming from. That's me deriving it. This is why this one was particularly nasty. So you have to remember this formula, because if you don't, cooking up the height out of that drawing of the equilateral triangle where you don't actually have an expression for a side length kind of stinks. Right? You have to use 30, 60, 90 triangles and remember a bunch of geometry about like angle bisectors and isosceles triangles, and it's not a lot. But this is nice. All right, so I just need an expression for L. Oops. So L is just going to be top y coordinate by minus bottom y. So my volume, the integral of 1/2 L squared dx. And since we're integrating with respect to x, we start slicing vertically at x equals 0, and we end at x equals pi. So if I wanted to try to do this, I'm going to have 1/2 integral sine squared dx, and what's the antiderivative of sine squared? Not one of our rules, right? Okay, so I can u sub that, right? No, because the derivative, if I use sine as my u, the derivative of sine is cosine. I don't have a cosine in there. Well, I can use some trig identity then. Yeah, probably not. Maybe the power reducing identity would, no, there's no cosine in that either. What do? Yeah, it just has to be a calculator problem, because remember, boop, 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 boop. In fact, there's no way for you to do, to do this without the calculator. They want, in fact, they're forcing to make sure that you know what to do with it. So this is me typing it in, and there it goes. I think I miscopied this, yeah. This is supposed to be 3 over 4, dum-dum. What do you guys think? It's okay. Notice that, again, me being able to visualize the solid, not terribly helpful to me. I can do this all without it just because of the instructions that they've given to me in words. They took out most of the visualization that is helpful to be able to do. They just removed it from me because they gave it to me in words. While you guys are, while I'm passing these papers out to you, I'm going to play this here at the end of class.
You're already familiar with finding the area
to let you get a better idea of
You're not
visualizing what's
actually
happening in this kind of
For
thing.
example, we could find this yellow area using a definite interval.
Because
Or we're gonna
old
do
Con
something
here does a
even
much better
more
job at
interesting.
drawing than I do.
We're going to find the volume of shapes where the base is defined in some way by the area between two curves. And in this video, we're going to think about a shape, and I'm going to draw it in 3 dimensions. So let me draw this over again, but with a little bit of perspective. So let's make this the y-axis. So that's the y-axis. This is my x-axis. That is my x-axis. This is the line y is equal to 6. Right over there. Y is equal to 6. And this dotted line, you can just draw it like this. And so this would be the point x equals 2. And then the graph of y is equal to 4 times the natural log of 3 minus x would look something like this. Look something like this. And so this region is this region. But it's going to be the base of a 3-dimensional shape where any cross-section, if I were to take a cross-section right over here, is going to be a square. So whatever this length is, we also go that much high. And so the cross-section is a square right over there. The cross-section right over here is going to be a square. Whatever the difference between these two functions is, that's also how high we are going to go. This length, which is 6 at this point, this is also going to be the height. It is going to be a square. It's going to be quite big. I have to scroll down so we can draw the whole thing roughly at the right proportion. So it looks something like this. This should be a square. It's going to look something like this. And so the whole shape would look something like this. It would look something like that. Try to shade that in a little bit so that you can appreciate it a little bit more. But hopefully you get the idea. And some of you might be excited, and some of you might be a little intimidated. Well, hey, I've been dealing with the 2 dimensions for so long. What's going on with these 3 dimensions? But you'll quickly appreciate that you already have the powers of integration to solve this. And to do that, we just have to break up the shape into a bunch of these, you can view them as these little square tiles that have some depth to them. So let's make that into a little tile, this one into it that also has some depth to it. I can draw it multiple places. You can do this and break it up into these things that have a very small depth that we could call dx. And we know how to figure out what their volume is. What would be the volume of one of these things? Well, it would be the depth times the area times the surface area of this cross section right over here.
So I'm just going to pause this at this point because.
So what would be the area that I'm shading in pink right over here?
Because that's what I wanted you to see was just what the picture looks like, right? Is that's kind of what you'd be envisioning in your mind. Is it really necessary to be able to see that to do these problems? I don't think it helps a whole lot because the wording of the problem tells you exactly what's going on, the cross-sectional shape you need, where, like the side length is in the plane, and you're just like, okay, like they just need to know the area of a square or whatever, and like, doodly-doo, I'm done. But if, like, at the, at the conceptual level, it helps to at least be able to visualize, oh, I see what they're talking about now. Doesn't really help me set up the problem any better, but in terms of like understanding what I'm doing, it's nice to be able to see. It's like, oh, okay, that's what they're talking about. You know what I'm saying? And he's a much better drawer than I am. Like the forced perspective in 2 dimensions is just like, didn't ever art that good. So, yeah, so I gave you guys a packet. There's, I don't know, what is there, 10 or 12 or something? Yeah, 12 problems to do. These are all AP style multiple choice problems based on this technique that we've used. You should treat these as homework. They should be something that gets loaded into your OneNote at some point. Should show some work on them. Try to work through them to your best of your ability. Obviously, we'll take questions. We'll do some more practice on this topic. I think I only get to see you guys once next week because of conferences. So we're probably looking at finding some time next week to talk some more about optimization. Because the following week after that, I'd probably be wanting to do our optimization little mini test guide. So just kind of keep that on, put that on your radar if you haven't spent some time to kind of get up to speed on optimization. We'll be looking at that the week after next. If you still have the test 5 makeup assignment to kind of get through with your partner, try to find some time next week to come in and work on that some more. Some of us have finished, and as you finished and I've checked your stuff in, I've been entering scores in so you can see like, oh, I got a grade now for this. Those are just kind of come in as you guys complete them and I get a chance to go over them. But that's kind of it for now. Everybody feel okay? So I think that you guys have already turned in 6-2, right? So for Sunday, the only things I'd be looking for is really the 6-2 delta math. If you haven't finished that yet, that should be done by Sunday, and I'll enter those scores in. We'll say this is part of next week's problem set. You don't have to finish this by Sunday. That's might be a lot. Helps to go slow. But that's kind of what's on deck here coming down the pipe. I think we have, for test 6, I think I just have 2 more sections that I want to do before test 6, so that's will happen before spring break. Okay? So put that out there as well. We still have to talk about 1 more volume technique, and then we have to talk about like work and accumulation, and then we're going to do some more targeted review, but that's 2 more topics, and it's test 6 time. Remember, we delayed test 5 and did some of test 6 stuff while we delayed test 5, so they're coming much closer together than is typical. Just giving you a heads up of kind of like what's your future's going to look like. I'm sorry if that's upsetting to you. We'll find some time to work on some stuff. Okay? So I think test 6 is going to be like, one part is basically just doing volumes, and the other part is going to be the rational function integration, and then work / accumulation.
Did you say test 6?
I don't have it, probably before spring break, but I don't have a date set.
After our June.
I don't know yet. I have to look at the calendar. I mean, we can set it for whenever you like. It just might mean I start test 7 stuff while we're waiting to do test 6, which I don't care. It's fine with me. If after Irish Week is much more convenient for you, we can talk about it when we get time to set a date for it. But we're doing fine time-wise, so we don't need to like bulldoze straight ahead as fast as I can. I can take some time here. We have a class period or 2 where we can slow down a little bit and like do some specific review stuff. Specifically, the volume stuff tends to be something that like you just need some time and some rep on. So again, yes, sir.
How long do we have to finish the test 5?
Corrections?
Yes.
I mean, I would love to have them before we leave for conferences by Wednesday of next week. But if you're not able to do that, I realize that I'm asking you to come in outside of class time to do it. I will not hold that against you. If like I still, I tried and I got in here and I've done some of it, but I'm just not as far along as I'd like to, and I'd like more time still. I'm okay with that, but like let's try for Wednesday of next week. Does that feel realistic?
Yeah.
Okay. Again, like if it doesn't happen, like I get that people are busy and I'm asking you to do stuff
Yeah.
outside of class time, and we'll be really accommodating on that.
Okay.
But we gotta get it done at some point, right?
Yeah.
You're welcome. Good job on your project. You're welcome. And you guys can go. I think there's no bells or whatever, so I've been talking for an additional minute. I'm sorry. You're welcome. I owe you a minute.
Yes, I can't do Wednesday, crap. But I think we should finish on Tuesday. Yeah.
Came in and took it to lunch.
Thank you.
Thank you.
You're welcome, girls. Thank you.
Mad because that one coach, Coach Blaze, they said that he was a betting me. He's like,
No,
that's
Lacey,
when
that pissed me off. What is
When Blaze said,
I got so much.